Okay, in this section we're going to talk about alternating series. Here's an example of one. With an alternating series, the signs of each term alternates. Oftentimes with an alternating series you'll have this little negative 1 to the n factor here. And it turns out there's a way to determine convergence if you have an alternating series. That's pretty simple actually. If you have an alternating series, notice these b sub n's, these guys. The b sub n, think of the b sub n's as the terms with the negative alternating part taken away. So the b sub n's are always positive, okay? Anyway, if the b sub n's are getting smaller, monotonic decreasing, and the limit as n goes to infinity of the b sub n's is 0, then the alternating series is convergent. So let's make sure you understand what this is saying. It's only if you have an alternating series, okay? Remember, we talked before, the nth term going to 0 does not guarantee you have convergence in general. Remember the divergent harmonic series, even though the nth term goes to 0, it still diverges. But if you have an alternating series, in this sense, isn't it kind of easier for a series to converge if it's an alternating series? Just has to satisfy these two conditions. So here we go. If you have a series like this, it is an alternating series. So if all it asks you is whether it converges or not, notice b sub n are the positive terms with a negative alternating factor taken away. All we have to do is show that these b sub n's are decreasing, and they are, because I think that's pretty easy to see in this case. This is b sub n plus 1, and this is b sub n. This is less than this because the denominator is bigger. So we got that. And then, does the limit go to 0? I think that's pretty clear too. That's obvious. Limit of this goes to 0. So the alternating series test says, therefore, this series is convergent. All right, this is a very important one right here. If you have the alternating, this is actually called the alternating harmonic series, okay? It's the harmonic series, but it has an alternating part here. It turns out we're going to show that this alternating harmonic series is convergent, even though the harmonic series is divergent. That's very important. This is a very important example. So b sub n, if you take away the alternating factor, is this. And again, I think it's clear that b sub n plus 1 is less than b sub n, and the limit is 0. So by the alternating series test, the alternating harmonic series is considered to be convergent. Let's do another one here. This one right here, let's see. For this alternating series, b sub n would be this. Now this is an example where it might not be obvious that it's decreasing. One way to show that it's a decreasing series is to look at the function f of x, in this case equal x over the square root of x cubed plus 1. Look at the derivative. Check me out that I did this right. This is what I get for the derivative. And since the bottom is always positive, the derivative is negative as long as x is greater than 1. The numerator will be negative. So therefore the function will be decreasing, which implies that the series is the b sub n's are decreasing. All we need to do now is show that the limit goes to 0. And again, you could use L'Hopital's rule here, I guess, but here I know some students in class, instead of using L'Hopital's rule, you could also divide top and bottom by the biggest power of n. In this case, it's n to the 3 halves. You see that? N to the 3 halves. Think of this as n cubed with a square root. So if you divide the top by n to the 3 halves and the bottom by n to the 3 halves, on the top you get 1 over n to the 1 half. And in here, I moved this inside the square root. It became an n cubed. Okay, you see that? I moved this inside the square root, so it becomes n cubed. And then when you divide each one by n cubed, you get that. That's how I came up with this, is I moved this inside the square root and divided each one by n cubed. So the limit then becomes, the top goes to 0, and this goes to 1 plus 0 on the bottom, so the whole thing is 0. So look, we showed the b sub n's are decreasing, and the limit as n goes to infinity of b sub n is 0. Therefore, this series is converges by the alternating series test. Now here's an example. This one might not look like a alternating series. It has that cosine n pi, but look, when n is 1, you have negative 1. When n is 2, you have 1. So this is actually just an alternating series. A sneaky way to write this, isn't it? So what is b sub n? b sub n turns out to be n over 2 to the n. And what do we have to show? We have to show that b sub n is decreasing. Again, I'm going to look at the derivative function here. I did a little bit of work here. You can check me on this. But the derivative of this function, x over 2 to the x, I get this, 1 minus x ln of 2 over 2 to the x. Why don't you check me on that? It's less than 0 as long as the numerator is negative. and that would be when x is greater than 1 over ln of 2. So that would, any time x is greater than 1, okay? So that would mean that the derivative will be negative, therefore the b sub n's are decreasing as well. Now, what is the limit as n goes to infinity of b sub n? I could apply L'Hopital's rule, and you get this, and then you can see that this is 0. So this series is also convergent by the alternating series test. Okay, let's do a couple more. Why don't you try this one? Can you think? This one's pretty hard. Let's better do this one together. This one's kind of messy. This is b sub n. Showing that b sub n is decreasing is kind of tricky. When we work with factorials, you got to really watch this. We're going to do this a lot, though, so pay close attention here when we work with factorials. b sub n plus 1, you replace n with n plus 1, so you get n plus 1 factorial, and you replace both of these n's with n plus 1, so you get this. By the way, what I'm doing here is I'm going to show that b sub n plus 1 is less than b sub n. That's what I'm doing. So notice this is another tricky thing. When you see n plus 1 factorial, isn't that just n plus 1 times n factorial? If you pull off the first factor, you realize you have n factorial left. That's a nice little trick. Secondly, this is just a bunch of n plus 1s, right? You have n plus 1 factors of n plus 1. So I'm just going to pull one of these off. I'm pulling one factor of n plus 1 off. What you have is n plus 1 times n plus 1 just to the n power now. Okay? Now, I can cancel the n plus 1s, and I have this. And then what I can do is realize, this is where you have to pay close attention to this. The reason why this is less than this, can you tell me why? Why is n plus 1, why is n factorial over n plus 1 to the n less than or equal to n factorial over n to the n? The reason is it's because the denominator is bigger. Isn't this a bigger denominator than this? This is n plus 1 to the n. This is just n to the n. So then it's less than this, which just happens to be b to the n. So that was a sneaky way to show that b sub n plus 1 is less than or equal to b sub n. When you have factorials, you really can't use the derivative idea because you can't differentiate n factorial very easily. So you would try this idea. So I've done half of it. Now what do I have to do? I have to show that that b sub n goes to 0, right? All right, I think we've seen this before. If you just write out what b sub n is, the top is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1, and the bottom is a bunch of n's. If you group these in the parentheses, I'm claiming what's inside the parentheses is less than or equal to 1, because notice the numerator is greater than or equal to the the numerator is less than or equal to the denominator, because each of these factors, see, n is less than or equal to n minus 1 is less than or equal to n, and so on. Each of the factors are less than or equal to the factors corresponding on the bottom. So the numerator is less than the denominator. So the thing inside the parentheses is less than or equal to 1. So this whole thing, if you keep the 2 times n squared there, I've showed that b sub n, it's greater than 0, greater than or equal to 0, since it's a positive term series, and it's less than or equal to 2 over n squared. The limit as n goes to infinity of this goes to 0, and this goes to 0, therefore this must go to 0 also by the squeeze theorem, right? So what have I got here? The reason why the series converges is because they're monotonic, the b sub n's are monotonic, decreasing, and the limit is n goes to infinity of b sub n equals 0. So showing that an alternating series converges is actually pretty easy, usually. And one last thing here. It's not only is that true, but it's also very easy to find an error bound. You know, when you approximate an alternating series, it's very hard to find what an alternating series converges to. In fact, that's true with all series. It's very hard to find the sum of a series unless it's a geometric series, right? Or perhaps a telescoping series. But even though you can't determine what it converges to, you can get an error bound for the alternating series. In the proof of the alternating series test, which we'll do in class, we're actually going to show that the remainder, or the error, which is you know, the sum of the whole series minus the nth partial sum, so what's the tail of the series, you could say, is less than or equal to the next term of the alternating series. So that's very simple. If you want to approximate an alternating series with a certain error, and the question is how many terms do you need? all you really have to do, this, see, like the error is less than or equal to b sub n plus 1. So what is b sub n? B sub n is 1 over n cubed plus 1. So what is b sub n plus 1? B sub n plus 1, remember the error is when you use n terms is less than or equal to n, b is less than or equal to b sub n plus 1. So b sub n plus 1 turns out to be this. And if you want that error less than 10,000, you could, well, one thing I did, I just flipped. If a over b is less than c over d and they're positive, if you take the reciprocals, this must be greater than that. That's a slick way to do it. Subtract 1, take the cube root, and what you end up with is n must be greater than or equal to 20.5, so you actually need n greater than equal to 21. That would do it. And that'll do it here. We'll see you next time. Bye-bye.